Hello everyone. This is BUSN 6630 Management of Operations Spring 2021 lecture. And this is Statistical Process Control. It's part of quality management. And so tonight, this is the topic for tonight. And I've already graded some assignments. An assignment is due this weekend, and this assignment is due after the break. And so actually, let me bring up the syllabus before we get started while I'm waiting for everyone to arrive. If I bring up the syllabus, we see down here that we're right here, April 13th, and this is in Quality Management Statistical Process Control Charts, which is very practical, which I'll talk about a little bit. But also, Quiz 6 was graded. Quiz 6 is going to be tonight, which is on EVA. A lot of people have already submitted it. And then the Quiz 8 is not due until after the break. And then, actually, this is the last lecture on material. And then we go into the review here. This review, I'll have class on Tuesday night, but mainly it's just any questions you have over the exam or the individual projects coming up. But this week I'll have a video for the exam and a video for the projects and presentations. So I'll have videos on how to do them after the break. And you have 3 weeks there to get things done. And the end of the course is Saturday, not Sunday, so be very careful you submit everything, because notice there's a lot of points here at the end. The exam and the project is 160 points, which is almost 40%, almost 50% of your grade. So here is a lot of your grade right here, so make sure that that's why I give you these 3 weeks here at the end to get it. So up here is where you learn it. Down here is where you validate what you've known, what you've learned, and show me. And also it allows me to post grades legitimately. Okay, that's where we are. Oh, let me open the chat room. Let me pop out my chat so people can. There we go. In case people want to chat, ask me questions. Okay. So first of all, I'll go ahead and get into the material here because this is going to be recorded. If we bring up Canvas, this is under Quality Management SPC. This will certainly be recorded and it'll be posted right here on Canvas, and so you can certainly look at this video. So I'll start with the video and the material, and as we get through the first part of it, I'll pause and see if there are any questions about any of the assignments that you've turned in, or any assignments that you've already turned in or you're going to turn in, and I'll see if there's any questions about that. Okay, so let me minimize this, and so let's get into process control charts. Well, also, actually, another thing, go back to the home page in Canvas and go to the website down here, mdharvard.com, and under Operations Management tab, if you come down here for the homework and also the lecture, this first video here is the first question in the homework. There's only 5 questions, and the other 4 questions will be the P chart, C chart, M chart, and R chart. And so these videos right here will tell you exactly how to do it and more. Okay. In other words, these videos these were made a long time ago, about 4 or 5 years ago. But this really does establish exactly how these things work. Okay. And also background and how to interpret them and this kind of thing. I'll talk about that today, but these go into a little bit more detail. And these are presentations. And so these videos are presentations along with the Excel spreadsheets. My lecture is going to be just a lecture. I'll explain it and also answer any questions that people might have. Okay, so there's where we are. Good. Let's bring up the notes in Canvas. Okay, here we go. First of all, there's a lot of material in quality control, and I as an introductory course, as a core course, as a broad treatment of quality control, I like to start with process control charts because it's very practical. The concept is as good as the technique, and it's something that you can always use no matter what you do. Large teams can do it, divisions can do it, but also individuals can do process control charts. Okay, here we go. And this is under the realm of statistical process control. And so therefore, in statistical process control, there will be some statistical basis in here and statistical terminology and statistical language. Okay, first of all, statistical quality control is made up of two main areas, process control and acceptance sampling. Over here on acceptance sampling, this is based on test of hypothesis in statistics, and process control charts are based on confidence interval theory. So this is confidence interval theory, this is a test of hypothesis theory. Now, I'm not going to go into the theory that this is based on, but because I'm not going to do acceptance sampling, I'll do just process control charts. But I will talk about, pull things from confidence interval theory and apply it here, and also from probability theory a little bit. But I'll show you how it's applied. Now, in acceptance sampling is usually by very large organizations, usually contract organizations. And if you are ever involved in acceptance sampling, usually you're part of a team. You're part of a large number of people that are doing this, and usually you'll have some quality control engineers or statisticians, and they know this pretty well, and so they are able to do this. But conversely, statistical process control can also be done by large teams. Companies, but it can also be done by individuals, okay? And this can be done on your work. And I've even had students come back to me and say their reports, they used process control charts in their reports for their annual reports on their progress, especially if they're doing sales or something. And it says it went over very well because you can actually see how well you do compared to other people. Anyway, and now in turn, they are broken up into different types of acceptance sampling plans and process control charts depending on the measurements. So variables are continuous measurements and attributes are discrete measurements. So you'll have variable sampling plans and attribute sampling plans. Also, you'll have variables and attributes in process control charts. So in this lecture, in this development today, I'll be talking about two types of variable process control charts, the M chart, which is mean, M stands for mean or average, and the R chart, R stands for range, or the range of a sample. And the attributes over here is the P chart, and the P stands for proportion of attributes, and then C stands for count, or the frequency of attributes in a sample. And so that's the chart, the four charts we'll do tonight. And if you understand these two for variables, two for attributes, then you really understand how to apply it. You'll understand, and also the first example, the concept, how to apply it, how to interpret it. Again, I want to encourage you to watch video number 1 because it does talk about all of that. Okay, let's get the concept. Here's the concept down. Suppose you have a process, and in this process it generates output. In this case, you can generate either a product or a service. And this product could be a computer, it could be an automobile, it could be any type of machinery, a mechanic, or any type of software even, or it could be services. And that product then would be a satisfied customer. And you conduct a service and you have a customer. Well, within the product or the customer or the service, you have a number of what is called quality characteristics. Quality characteristics. And these quality characteristics really refer to variables that are measured, like the durability of something, or the speed, or the voltage, or something about the size, the length, does it fit, how much clearance is there. And so automobiles can have miles per gallon would be a quality characteristic, high, low, or something like that. Or it could be qualitative. It could be prestige, or something like brand or value to the customer, or image, especially in clothing. And so, but you'll have a number of quality characteristics. So in these quality characteristics, you have a measurement, a metric, and in that measurement, you'll have ranges of good and bad. You know, is it good or is it bad? And so what you do in statistical quality control, you will take a sample of size n during production. This is a production process. You take a sample of size n of that quality characteristic, and there could be many of them. But that sample of size n, when you measure it, that will tell you, or that will indicate either good quality or bad quality. In other words, it's in the range, it's not in the range, whatever. Good quality or bad, and we'll look at 4 different measures today in just a second. Just not, well, more than a second, this evening. Anyway, either good or bad. Now, if it's good quality, then nothing is done and let it go on to the customer. But if it's bad quality, then there's 2 things you can do. One is statistical process control, where you examine the quality characteristic from the sample on the sample SPC chart and make inference about the control of the process. In other words, you say this is bad quality, therefore the process is out of control. The process is out of control. That's one way to do it. So then you go back and try to find the cause of it. The second way to do it is acceptance sampling, where you compare the quality characteristic here from the sample with an acceptance number or a rejection number to make a decision about a lot or a sample. Sample, lot, same thing. In other words, you have the bad, okay, the good and bad, it's bad, but then how bad is it? Okay, you'll have different levels. Okay, if it's in the first level, then you report it. If it's the second level, then maybe you reject it. If it's the third level, then maybe it's rejected and it's reported, and maybe you'll never really, you go back and rework some things. In other words, but the acceptance sampling focuses on the output. It doesn't focus on the process. So acceptance sampling looks at the lot. It makes a decision about the lot. Do we accept it or do we reject it? And if we reject it, how do we reject it? So that leads you into a whole different type of analysis. If when you reject it, what do you do? And we talk about this in supply chain analysis and reverse engineering. Reverse supply chains. When it goes upstream, a reverse supply chain, what do you do with that? Oh, there's a lot of things you can do with it. But in quality control, all you're saying is I'm rejecting it. I'm not letting it go to the customer. Whoops, not letting it go to the customer. I'm rejecting it. So we don't get into that because it's a whole different type of analysis. But we will get into these process control charts where you analyze the process. Now, some people say, well, why wouldn't you always want to improve your process? Well, sometimes you don't want the people who are doing the acceptance sampling to have access to your process. Remember, I said this is very large organizations, large contracts. A good example of this is like, let's suppose Ball Aerospace or Lockheed Martin. They have a contract with a technology campus, technology center, and they're a funding center. So they fund them to do projects to give widgets or O-rings or something to NASA or to some other military or something. And so they say, okay, well, we want to measure this to make sure it has quality. And so the acceptance sampling says, okay, well, if there's bad quality, then they will not accept it. But you don't want them to come into your shop and look and find and say, you need to improve this and this and this, because they don't know what you're doing. We have done MRP, and this is a true story. A true story. Years ago, I was talking to a person in one of the major production facilities around here in Denver, and they told me a story. I was at some seminar or meeting or dinner meeting or something. Anyway, he said, well, we had someone from the funding agency come, or even their client came, and he says, oh, I'm here to inspect your operations, okay? And your operations, we had acceptance sampling, and so we want to inspect, actually it was pre-contract, inspect the MRP and how you actually generate this stuff? And they go, sure, fine. And we chit-chatted for a while. We talked. And he says, okay, you're ready? And the inspector from this organization said, oh, yeah, but I have one question before we start. And he goes, okay. He said, what is MRP? I said, okay. So he says, well, he tried to explain it. They looked around, and he left. And he said, and so really a lot of times these people know their job, but they don't know your shop. And so that's why acceptance sampling sometimes is preferred. Now, process control charts, where you go back to the process, that's where you do it yourself, in-house, because you know your process. So that's how these are used. Okay, so now let's go on and see how it's done. Introduction. Now, the objective of a statistical process control chart is to measure a quality characteristic over time to infer the control of a process. Okay, now, the process control charts measures and says, oh, I'm going to infer. You don't say, oh, it's out of control. You say, oh, this indicates that it's out of control, or I'm inferring that it's out of control. Big difference, because you could say it's out of control, but maybe it's not. Maybe the measurement was wrong. Maybe the instrument was wrong. Maybe you reported it wrong, but you're inferring that it is, and you're investigating it to see what's going on. Okay. We'll get back to that. Well, that's in the video, so watch the video. The procedure of a statistical process control chart is simply this. 4 steps. 1, conduct a statistical experiment on the process, experiment, not production, experiment on the process that is in control to obtain a random sample of the quality characteristic. That's a big sentence. That's a very important sentence. It's a sentence, and this sentence is where a lot of people make mistakes. First of all, a statistical experiment, not an ad hoc experiment, not an experiment that you casually, conveniently sample, an actual statistical experiment where you're focusing on a quality characteristic and how that quality characteristic impacts the quality that characteristic should be measuring. 2, that's one. That's 1. 2, the process is in control, and that's extremely important, and I'll allude to that today with some examples. The concept is simply this. Make sure your process is in control, and then when you see it generate output, you know what that quality characteristic looks like when the process is in control. So this is what it looks like when it's in control. So now in the future, if it doesn't look like that, then you're going to infer that it's out of control. That's pretty simple, but it's not obvious. A lot of people don't do it that way. 2, to obtain a random sample of the quality characteristic. And I just want to say here, let me underline that. And I just want to say here, one of the first jobs I had when I left school was experimentation and sampling and doing experiments and etc. And that was such a great job. It was really, really enlightening because in school, you're given a random sample and you don't even question it. Well, let me tell you, being there on the ground, boots on the ground, there's no such thing as a purely random sample. There's always error in there, that some of it should be there, some of it should not be there, that there's no such thing as a pure random sample. You're going to have factors in there, and that variability just keeps growing and growing. And a lot of statistical analysis and statistical theory is trying to find the factors that contribute to that variability to reduce the variability. That's systematic error. Okay? And so therefore you try your best to obtain a sample as random as you can. Why? Because you're focusing on the quality characteristic. Now what I mean by random is you'll have unexplained variability, but in the experiment you want to control that as much as you can so the variability is small as possible. That's one thing. The second thing is if you have no variability, there's a problem somewhere. You haven't measured it right, or you haven't reported it right. So don't look for zero. That's a red flag. Okay. That's one. Two, estimate the parameter used to calculate the values in the control chart. Okay, and so the second is going to be estimating parameters. And that's what I'm going to be talking about on those four, the PC, M, and R chart. We'll be estimating parameters. And there's where the statistical theory comes in. Three, select a sample size, determine the values, and construct a control chart where you'll have a center line, an upper control limit, and a lower control limit. And the upper control limit is going to be, the actual definition is the mean of the random sample. Actually, the parameters here in this case are the mean and the standard deviation of the mean of that random sample. And so the upper control limit is 3 standard deviations of the mean above the mean, and the lower control limit is 3 standard deviations of the mean below the mean. Okay, so there's the 3 things we'll be looking at today. And so that's the mechanics. Okay, one mechanic is getting the parameters, and 2, taking those parameters and generating a chart. Okay, and then you interpret it. Okay, and then once you have your chart, then you move away from the experiment and you monitor the quality characteristic of production over time to infer process control. Now we have production. Okay, up here we have an experiment. Down here we have production. Now, an experiment and production, I want to distinguish the difference between those. Some people put them together, and you can, but I'm going to distinguish the difference mainly because the data are handled a different way. They're not handled the same way. And so you have your experiment to estimate your parameters, then you have production to infer process control. Those are 2 different objectives. Estimate parameters, infer process control, 2 different operations. Okay. Let's go in and do it. Okay, now to separate this out, to take these 4 steps, define quality characteristic, define, and this we'll talk about this on all 4 of these things, all 4 of the process control charts. Draw a random sample, and I'll just give you the random sample again, just like a textbook. Estimate your parameters. Now there's where your experiment is, and then you move to constructing your chart, and constructing a chart with a sample size. And you determine these values as center line, upper and lower control limits. And once you have it, then you monitor production over here and infer the control of the process. So here's what it looks like. You'll have a center line here. You'll have an upper control limit, lower control limit. And then over time, you'll start plotting values. As production comes out, you measure, you take a measurement sample, and you plot it here, and it's a plot. Just bing, 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 bing. And so let me take this. I'll erase it because I don't want too much in here. Let's see here. Here we go. And so you have boom, 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 like this, and you plot as you go along. And so if it's in here, you're fine. But if it comes up here, oh, that's not good. Okay? Or coming along, and it comes down here, well, that's not good, okay? And so all of a sudden, there are different ways that your process can be out of control. It can be above the upper control limit. It can be below the lower control limit. It could be a linear trend. What you want to see here is a random component, no more. You can have a trend component, that's not good. You can have a cyclical component, that's not good. It can be outside these limits, that's not good, on and on and on. The video explains the anomalies, and there's a number of them, okay? But before we go on, just a little bit glimpse into how these are used. Suppose the pharmaceutical industry is looking at a new medication or drug, and we've seen that. And in this medication and drug, they have a process control chart, and they want to make sure that it's within the control limits. So they're coming along here. Actually, years ago, when they had generic drugs, they had to recall them because some of the generic drugs didn't have enough of the active ingredient. They had a lot of the inactive ingredients, but not enough of the active. That was years ago, 20, 30 years ago. Anyway, suppose you're going along and the active ingredient is below what it should be. Okay, so what's the risk of that? Well, the risk could be you're not going to get well, you're going to stay sick. On the other hand, if it goes above and there's too much of that active ingredient, what's the risk? Well, if there's too much, the risk is you could die. So the risk going above and the risk going below are not necessarily the same. So they'll have different protocols if the control chart is violated a certain way. And that violation then will move, and you make a decision, you make an inference, then you move to a protocol, and that protocol could be very serious, it could be minor, it could be just reporting, it could be anything. Okay, so it'll have different risks. That's what I'm getting at. Okay, so we'll be looking at 2 attribute control charts, P and C, and 2 variable control charts, M and R. So let's do them. Let's get into it. That was my introduction. I should have music. I should have interlude music right there. Good question, Craig. The plus or minus 3 standard deviations is standard in textbooks, and that's pretty much what Deming or Schuhart. These are called Schuhartian charts. Walter Schuhart and Deming use these. That's what they introduced initially just to start. If you don't know, just start it. But then after you use these control charts a lot, you're beginning to realize your application and that specific quality characteristic, like I said, the risks are different. Well, if the risks are more severe here than here, then you might want 2 standard deviations or 1 standard deviation. And it's much more sensitive then. And if some of them, it's not that big of a deal, maybe 3.5 standard deviations. So the risk isn't that great. Remember, risk is probability and also the consequences of the probability. And so if the consequences are severe, like death, well, then you may not have 3 standard deviations. It might be 2 or 1.5. And so so it's a good question. But we don't get into that here. That's when you start applying these things, and that's when you started using these things in real life and in reality, in the real world. And every application is different. Okay. P chart, control of a proportion. Okay, now P stands for the proportion of a quality characteristic. So this, okay. Now what I'm going to be doing is giving you the introduction up here on when you use it and why you use it, then the experiment right here, and then I'll construct the chart right here, and then down here is the production. So I'll do that on each one of these. Okay, first of all, when do you use a P chart and why do you use a P chart? Well, the P chart is commonly used for the detection of an anomalous proportion of a given attribute characteristic from a known sample size within a service operation or manufactured product. Okay? The data are assumed to be drawn from a binomial probability distribution. And the binomial distribution for this development is characterized by only 2 outcomes per trial, constant proportion of success, independent trials. So let me not just say these glibly. Let's talk about those. Okay. First of all, a binomial experiment. Bi means 2. Nomial means nominal. 2 nominal outcomes. So they're not ordinal. They're just nominal. For example, the classic example of this is you flip a coin and it's either heads or tails. That's a bi outcome. The trial is flipping the coin. The outcome is either heads or tails. It's a bi, it's 2 outcomes, and it's nominal. That's a binomial experiment. Okay, and so number 1, only 2 outcomes per trial. Well, when is that used in reality? Well, it's like, okay, does it meet standards or does it not meet standard? Does it leak or does it not leak? Is it broken or is it not broken? You know, is it good or is it bad? Is it acceptable? Is it unacceptable? And so the binomial distribution happens quite a bit. Like, I don't care how bad it is. If it's not going to work, it's not going to work. Give it an inch. It doesn't matter if it's an inch bad or a mile bad. It's bad. So it's either binomial. It's either good or it's bad. Okay, acceptable, unacceptable. The second is a constant proportion of success. Now, the binomial experiment, one trial is one flip of the coin. Now, you're not just measuring one at a time. A lot of times you're measuring a known sample size. Suppose you're measuring these bottles has a fluid ounces here, or maybe the cap on top of it here is once it's put on, does it leak or does it not leak? That's binomial. Yes, it leaks, it's out. No, it doesn't leak, it's good. Good, bad, good, bad. And so, but the machine that comes down and goes and puts it on, boom, and then you measure it. Oh, it didn't. Oh, shoot. I got water all over my. I didn't go all the way down. Oh, man. Okay, I didn't. I missed my computer. I gotta stop. Sorry. Where was I? Oh, that the machine that does this should have the constant proportion of success. In other words, when it's operating correctly, it'll always do it consistently. Okay. Now, once every 500 or once every 200, once every 1,000, it may not do it right. Okay, well, that's what we're trying to measure. Nothing's perfect. How imperfect is it? Well, 1 out of 1,000, 1 out of 5,000, 1 out of 100, 1 out of 12. Well, this machine, it's in control. That's how good it is. So when it's in control, we're measuring how good it is. Okay, and so the lower the probability or the lower the number of defectives, the better it is, right? 1 out of 100, 1 out of 2 every one of the one. That's not very good. 1 out of 100, that's pretty good. 1 out of a million, 1 part per billion per million, that's really good. Anyway, that's the idea. Okay. Now that's the second one. Now the third one is independent trials. Okay, now the independent trials, I'll try to do this again and be careful. I get excited over this stuff. Close it. Independent trials is that when you measure it, that trial is independent of the next trial. Is independent of the next trial. Each of these are measured independently. In other words, suppose this is measured, okay, and it spilled, which I just did, okay, and then the next one is measured. Well, it's not cleaned up, and so it says, oh, there's water here, or there's tea. This is tea. There's tea here, so therefore this is bad. But it's not, because it's dependent on the one before it. And so the trials are dependent. You don't want that. In other words, the outcome of one trial influenced the outcome of the other trial. And so the second one wasn't bad, but the first one was bad, but that influenced the other one. So you have to be careful of independent trials. So first of all, this is the design of the experiment. This is the process, and this is the measurements. So those three are very good indications of looking at the statistics, the foundation of the statistical theory, and when something doesn't work, then this is where you go to find the cause. Okay. Okay, let's do the experiment. Consider the following results of an experiment from a process assumed to be in control again. Now, there's two things. There's two things in experimental design. One is the number of samples. We have 10 samples. The second is the sample size. Okay, the sample size is 5140. Now, these have very specific definitions, okay? Now, when you start practicing and start working, you can define these any way you want. This is the original, this is the traditional way these things are defined. We're looking at these tops. This is an experiment, and so the sample size is 5,140 of these tops. It goes zzz, 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 zzz. They do 5,000 of them, or 5140. And that's called sample one. So the first sample is that many items. So the sample size is the number of items or the number of measurements per sample. Okay, the whole experiment is 10 samples. And so if each one of these have a sample size of 5140, then the experiment has 51,400 because there's 10 of them. So 51,400 is the total number of observations in the experiment. But the sample size in the experiment is 5,140 because that's how many measurements there are per sample. And the number of samples are 10. Be very careful with that language because you'll see it on the homework and you'll see it in industry. They do talk about that. Okay? Okay, we're measuring 5,140 of these things. And out of that, you know, when you measure that many, you keep track of how many were defective. Okay? In this case, the attribute was a defective top. So our attribute here was defective top. It could be other things too. It could have a crack in it. It could be all kinds of things. Anyway, here's how many they measured out of 5140. These are the measurements. Okay. Now, remember for the experiment, we're trying to estimate a parameter. Well, the parameter we're trying to estimate is P. That's why it's called a P chart. P is a proportion. So what proportion in this experiment were defective? Well, I have 1,080 out of 51,400. So I take that ratio and that average proportion, that P, that proportion, that's my average P. That's my average proportion, which is my parameter. 0.021011673 or 2.1%. Notice the experimental design was samples and sample size. We didn't use it. It doesn't matter what these are. These could be 5 samples of 10,280. If you got the same results here, these last 2 results down here, this is the only thing you need for the P chart, the way I'm presenting it in this example. Okay, now that we have the proportion, this parameter, now from the experiment, we copy it down here, and there it is. Now we construct the chart. Okay, now let me back up here and review a little bit right here. Now this sample size was in the experiment. And the reason for that sample size, usually you take a sample size as large as you can, because the larger the sample size, the smaller the error in your estimate. And so that sample size is in the experiment to get a good estimate of your parameter. This sample size is for the chart. And usually this sample size is determined from the production process. Okay? So down here, notice my sample size is 1,285. Well, that's from the production. Maybe I should have had a probably smaller one, but let's suppose that they do 1,285 of these at a time. Okay? In 642 and a half or whatever, or divided by 5, and what's that? 257. So that's how many are in each box when they ship it out. And so they're going to measure that. Okay? And then they stop, and then they report it. Okay? So this comes from the production process. Another example of this, which I like to give, is you buy a 6-pack of Diet Dr. Pepper, let's say. And I've been known to drink a Diet Dr. Pepper or 2. So you buy a 6-pack. Well, wait a minute. Did it go through quality control? Yes, it did. Well, if you measure 1 bottle at a time, each bottle and report it, the sample size is 1. People don't usually do that. But if you measure 6 of them and then report 6 at a time, well, the sample size then is 6. But if that 6-pack goes into a carton of 4, so you have 24, then measure that one. I mean, you measure all 24 bottles, but you report it 24 at a time, then the sample size is 24. And that 24 goes into a pallet of 10 of them. So now you have 240. So the sample size for the chart depends on where you're reporting it. You're measuring them, but then you're accumulating them and then reporting them. So that comes from the production or the services. Okay. Okay. Now, remember, in order to generate a chart, we're going to need a. Let's back up here. Come back here where we did it. We're going to need a mean, and we're going to need the standard deviation of the mean. Those are the two parameters we need. The mean and the standard deviation of the mean. Those are the two we need. Okay, so where do we get them? Well, when you have a binomial experiment, you go to the binomial theorem. We're not going to get into the binomial theorem, but we're going to have results from the binomial theorem. Okay, we'll estimate of the average proportion, and that's the standard deviation of the mean, is the square root of p bar times 1 minus p bar over n. Now you say, where did that come from? It came from the binomial theorem. And so you go into the theory, the statistical theory, probability theory, and you can define it, and then you develop it, and then you estimate it, and all kinds of stuff. Well, that's given to us. We don't have to go in, we don't have to derive these things. It's a business course. But that is the standard deviation of the mean, which is the average proportion in this case. That's the estimate of it. Okay, let's do it. Square root. I bring down the 0.21 right here, times 1 minus 0.21 divided by 1,285. That's the sample size of the chart. Notice the sample size in the chart goes in the standard deviation. There it is. Up here, the sample size of the experiment is used to estimate the parameter. So the sample size of the experiment is contained in the p bar. It's in the 0.021. The sample size for the chart is contained in the standard deviation. Okay, so you have your point estimate, your mean, but the variability of that mean really determines the variability that's going to be used in your chart. There it is. That's the explanation. Okay, now that we have it, the center. Oh, notice here though. Notice I picked these numbers because it's 0.004000099. Okay, there's probably more significant figures than that, more figures than that. But notice I have the p bar is 0.021011673, but down here I just said 0.021. But then over here I have 0.004000099. So there's a rule here, a strict rule that you use for this course, and I highly recommend you use this in industry. Never use a rounded number for calculations. You can round it to present it. Say, oh, it's 2.1%, it's 0.021. That's fine to talk about it. But if you use it in the calculation, use all the significant figures you can use. Because if not, then you have something called tolerance stack up, and it's going to Greg, the sample size from the chart comes from the production process. Okay. So always use all the significant figures when you calculate. And I gave examples of that, Craig. So you look at the video. I gave examples of. It depends on how many you aggregate to report. You can report one at a time. That's n equals 1. Or you can have 1,285. You wait until you measure 1,285 of these bottle caps, and then you report it. Okay. Okay. Now we have the center line and the upper lower control limits. P bar plus or minus 3s. P bar is 0.021. 3s is 3 times 0.004. And so I do the arithmetic. Now, again, I represent this with 3 significant figures, but I use all the significant figures, all of them. Then I round it. Okay, 0.033, 0.009 with a center line of 0.021. Okay, there's my center line. I've constructed my chart. Now I go to production. So once I have this is an experiment. This is in the quality control department. Now that you have the chart, now you take it to the shop floor and say, here's a chart, ready to go, measure production, and post it to the control chart. Okay, so here comes the tops. Consider the production plotted on a P chart for N equals 1285. Okay, the lower control limit, upper control limit, and there it is right there. And so here's the 1285 sample size. Here's the number of attributes that were measured as you reported them. And then you take the attributes, divide by the sample size, get a proportion. And so it's normalized. Okay, so you don't have to worry about thousands and thousands of items. It's just a proportion. That's a lot easier to manage. And so you plot it. So this right here is plotted right here. Up, down, up, D, 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 D. So what you want to see right here is a random component. No more, no less. Now, we're not going to get into that in this course. But I urge you, when you leave here, you should know this. I urge you to, if you go to the, go back to home. If you go to the website, Operations Management, and come down here to Statistical Process Control Charts, video 1, please watch video 1, because video 1 talks a lot about how this is used. Okay, and this is not for necessary academia. This is more for industry. This is how you would do it, and to review when you're doing it in industry. Okay, and these others down here are just mechanics on doing the charts. Okay. Now, as we go through here, we say, okay, this looks pretty good. This is right here is close to the line. See, which one is that one? This is 0.033. Oh, it is on the line. It's right on there. Anyway, that's fine. But if it's on the line, is it in or out? It's in. It's in. It's kind of like tennis. Okay, when it's on the line, it's in. It has to be over the line to be out. Okay. Anyway, and we'll talk about that on the C chart as well. So that's what you do. So then you'll have different rules on how to interpret or just make decisions about the chart. In other words, what if you had all these which were way too high up here, or you had a linear line, and so this went down and went 5 or 6 of them in a linear line. Okay, you'll say, well, when I see that, even though it's inside here, that's not random. That's like a linear trend. Or you have a nice seasonal, a nice cyclical comp. That's not random. That's cyclical. Something's going on. So what you'll have are different decision rules are used to make an inference about the control of a process. So the decision rules, they have a list of rules. And when you look at the manuals, and some of these manuals, they'll have on a control chart, they'll have anywhere from 2, 3, 5, or 8 or 10 of these things. And so when you look at that, you get used to saying, oh, yep, rule number 8, and so therefore you report it. And so quality control looks at this, okay, we need to go back and do something about it. Or not, it depends. But anyway, the decision rules, there's a number of them. And these decision rules are rules that are established to make a decision about the chart to say, boom, there's an anomaly. And it doesn't, and it's used to infer the process. It doesn't necessarily say the process in control or out of control. It's that this chart has a decision rule that indicates the process could be out of control. It's inferring that. You have to go back and actually investigate it. Well, how do you investigate it? Well, that's the next thing down here. The method of assignable cause assigns anomalies in the control chart to causes in the process. In other words, here's a chart, there's an anomaly, something's wrong, you report it. Okay, then what do? Okay, if all you do is report it and you never do anything about improving the process, then improvement never happens. And some people do that. So the method of assignable cause is I'm going back to the process and trying to identify the cause of that anomaly and see what the connection is. Now, the method of assignable cause can do a lot of different things, and I go through it in more detail in the video, and it goes through all different ways of doing it. There's you can do it in the experiment. You can do it. You can do it in the reporting, in the production. So either you can do it in the design, or you can do it in your production. You find an anomaly, you find out the reason, and then you document it. Anyway, there's all different ways of doing it. But somehow you should go back and say, what's the cause of this thing, and then improve it and change it, and then you go into configuration management. Okay, so before we go on, we are at a place now to talk about quality control programs. A quality control program consists of three stages. The first one is quality planning. Quality planning is everything, the experiment, measuring it, the chart is just everything before production. Okay, that's quality planning. Now, I'm defining quality assurance as, and I do it in the video, quality assurance is assuring that this chart is the measurements are done correctly, the proportions or the data is recorded correctly, it's reported in the chart correctly, the decision rules are done correctly, and in other words, the assurance is assured that the plan is done as designed. And you measure it, you have the inferences, you report it, everything around the control chart, process control chart, everything is done correctly. That's assurance. Now, quality control, on the other hand, is saying, okay, this method of assignable cause indicates there's a cause there. Now what do? Well, you go back and improve the process. That's quality control. Quality control is actually changing the process, improving it, and there you have configuration management, change management, and that is a lot more difficult than you think. Okay? Or quality control is auditing the process. Is this process, you might be doing it correctly in assurance, okay, and the plan was correct, but the quality control will go back and have an audit of the process. Was the process designed correctly in the first place? Is it doing what we thought it was going to do? We thought it was going to be doing, or do we go back and redo the experiment? So quality control is looking at how this moves toward improvement. Okay, and so so these three things, and as I say in the video, some people put these together. They call this QA/QC. QA for quality assurance, QC for quality control. Some people say QA/QC. Some people say QA. Some people say QC. Some people just say quality. There's no standard names, but the planning, assurance, and control is pretty much what the American Society for Quality Control introduces it as, and also Project Management Institute does quality that way. So a lot of the institutes, conferences, and organizations will have that definition or something very close to it. Whatever you call it, you can call it ABC if you want. Whatever you call it, somewhere you have to plan it. Somewhere the plan has to be done correctly, and somewhere you have to go back and improve the process. Those three things have to be done, whatever you call them. Let's go a little bit deeper. Once the experiment has been performed, and let me underline that, the parameter does not change. Now remember the experiment up here. This experiment says the process is in control, right? It's in control, so therefore once we have this proportion, that proportion indicates that the process is in control. That's a parameter. Now different charts could be generated with different sample sizes. In other words, in the production line, let's say assembly line, you can measure different places. Like if you measure the 6-pack of your Diet Dr. Pepper, the sample size is 6. If you measure the pallet, it could be 240. If you measure the truck, it could be 24,000, okay? The actual semi-truck. Therefore, the parameter does not change, but different control charts can be constructed for different sample sizes using the same parameter. In other words, at different places in the process. Okay, consider the examples below where the parameter P is from the experiment and the sample size n is given. So I only did 4 of these things. I probably should do more. But look what I do here. So here's the point. Here's 2.1%. That doesn't change. Now my sample size, I'm going 1,300, 1,400, 1,500, 1,600. I increase the sample size. So what's going to happen? Well, first of all, since n is that p doesn't change, n is in the denominator of the standard deviation. What's going to happen to the standard deviation? It's going to decrease. 3.9, 3.8, 3.7, 3.5. It gets smaller. The center line doesn't change, but since s gets smaller, you're subtracting lower amounts from the lower quality, so it's going up. Lower amounts from the upper, you're adding lower amounts to the upper quality, so it goes down. So the interval then begins to decrease. 2.3, 2.2, 2.2, 2.1. So as the sample size increases, your control chart decreases. Let me say that again. That's key. As your sample size increases, your control chart decreases. So, logically, as the sample size decreases, the control chart increases in size. They're inversely related. That's important. Why? Well, that's where people really make mistakes, and this is where errors are made quite often. Since we're here, and I don't think I do this in the video, but let me do it here because I think it's important. Let me show you how this is done before we move on. So suppose that you are, actually this is not a true story, but it's similar to stories that I've had, like in conferences. You go to a conference, a dinner meeting or something, and you have all these quality control people there, and you sit at a table at a dinner meeting, and you're talking, how you doing? What do you do? And says, oh, I'm in quality control. So, oh, you are? Well, that's great. What we're at is I'm an ABC company over here. Oh, I've heard of that company. They're really good. He says, yeah, I'm the head of quality control. Wow, congratulations. He says, yep. I says, they do a really good job, don't they? He says, yeah, we do. He says, yeah, that's great. I've heard you got awards. Oh, yeah. We haven't been out of control. We have not been out of control in 10 years. I've won 3 awards. Really? That's really good. How did you do it? Could you tell me how you do it? He says, sure. Right here, in our production, our people are so good. They're really, really good. In our production, every single day, we have like 15 samples every day. And every day I take these samples, and from those 15 samples in our production, we calculate an upper and lower control limit, and we plot it, and we haven't been out of control. We have not been out of control in 10 years. Sounds good, doesn't it? Now, when I'm in class, and I look at your faces, and I say, did you catch it? Did you catch what he said? I hope so. But a lot of times you don't, because it's very subtle. Let me say that a different way. Oh, every single day I take our production, I take the maximum and the minimum, and I plot my points against it, and we never go above it and never go below it. Of course you don't. You're plotting the data on a chart generated from the data. That's not how you're supposed to do it. You're supposed to generate your data from production on a chart based on the experiment that's in control. Because if your production goes out of control, well, the chart goes out of control with it. Make sense? A lot of people do that. It's fascinating. They don't get it. And that's why you need business people doing business. That's why you need business people who understand business. That's why you need MBAs doing business, not people who don't have a business background. Because it's so easy to do it incorrectly. Well, they haven't been out of control in 10 years, he said. And so you explain it. He says, well, you know, that's not how it's done. Because if it's out of control, the control chart will be out of control with it, and the data and the control chart kind of go together. So you want a control chart when the process is in control, keep that fixed. And if your production goes out of control, then you'll know. That's how you do it. And he says, he thinks about it. He goes, oh, I see what you mean. Well, I'm not doing that. There's no way I'm doing that. I'm going to keep doing it this way. Why? He hasn't been out of control in 10 years. He's won 3 awards and he gets all the... No, he's not going to do it right. If he keeps doing it wrong... Now, wait a minute. 10 years and the company he works for never really saw that? Never really identified what he's doing? So there's a lot of wrong going on there, right? So he says, we're at the meeting. My boss is over there, so don't tell him. We take a break. We come back. Yeah. My boss over there, don't tell him. Well, I just told him. Oh, no. You told him. And so his boss comes, you're going to have to do an experiment on Monday. You're going to have to do an experiment. And I want you to plot this from an experiment. So he goes, he looks at you in disdain and says, okay. So he goes home and starts thinking about it. And so he comes and does the experiment. Okay? And so he says, 1285 is what I'm going to be using here. Okay? And so, I want to save the company money. So up here in this experiment, I'm not going to take this many samples. I mean, it's just way too expensive. And so I want to save the company money. So I'll take 10 samples, but I think each sample might have 100 in it. 100. Okay? So I might have 1,000 and that's all. Okay? And that's all. Okay? And so I say, okay, fine. And then down here, I'll measure the sample size of 1285, but then I'll construct my chart on 100. I'll use the sample size up here, down here. Why would he do that? Because if the 100, then what happens to the chart? It's going to be large. And so no matter what happens, in other words, it's not going to be this big. What's going to happen then? Let's bring another thing here. It's going to look like this. And it'll never be out of control. Why would he do that? Because he knows his boss just wants an experiment. He doesn't know how to use the experiment. And so do people do that? Do people do that unethical and well, maybe. He says sarcastically. So therefore, if you're a manager, know what's going on. And that's why this is an important lecture. Quality control is used everywhere. And I toured a facility one time, and they says I saw like quality control is number one, that kind of thing. It wasn't GM or Ford or anything, but anyway, it was ball bearing company. And so we walked in there, and so we're on a tour, and I saw the quality control department over there, and I said, "Is that the quality control department?" Yeah, that's what. I said, "It's all dark. What do they do?" "Oh, we do quality control." I says, "Okay, well, I don't see anything out here measuring anything." He said, "Well, they do it in there." "Oh, do they bring it in there to measure it?" It says, No. That's where they do the reports. So they do reports. "Oh, how often do they do them?" "Once a month." Well, what do they report?" "Well, that's not part of this tour. We'll just go on." And I never saw any indication anywhere that they were measuring anything. So they got data probably one day, go in there and report it. And, they're not measuring it. They're just reporting it once a month. And the reports look really nice. But the point is, I guess what I'm trying to say is, this is not difficult, but there's so many places where you can misuse it. And if you don't know what's going on, then it can be misused. And as a manager, as an MBA, recognize how this stuff is used and how it's misused. Okay, so that's that chart. So let's go into the C chart. C chart, the control of the count or frequency of a quality characteristic. The C chart is commonly used for the detection of an anomalous count or frequency of a given attribute characteristic from a service operation or manufactured product. The data are assumed to be drawn from a Poisson distribution, Poisson distribution. The Poisson distribution is characterized by a small probability of occurrence of an event in a defined interval of consideration. When the proportion of the binomial distribution is small and the sample size is large, the Poisson distribution is a good approximation. So let me explain this. This is really important. The Poisson distribution, as it turns out, is a very important probability distribution. And so this is statistics. This is actually probabilistic statistical design, statistical theory. It's not data analysis, it's statistics. In other words, Poisson distribution is a very important distribution. It can be derived many different ways. In this case, it's characterized by a small probability of occurrence of an event in a defined interval of consideration. Now, when I teach this in statistics, I'll say, well, it's like the probability of an accident happening during a day in Denver. So hopefully it's small, okay? And that's time. The interval of consideration is 24 hours or 12 hours, okay? Or it could be how many potholes are there on a county road, any random. Well, now that's length. My interval of consideration is a length, and my occurrence is a pothole, okay? Or it could be, what else could it be? It could be the number of colonies in, or actually the number of gold veins within a play, okay? Or because gold occurs in different pockets, and so that could be random. That could be a volume, okay? So you can have all different kinds of things. But in this case, it certainly applies. Oh, I used it back when I was doing risk analysis for the government on what's the probability of having an earthquake that was severe enough to damage a nuclear repository. You want to know that. And so if the probability, and that's a very small probability, but that is a Poisson distribution. Or if you have a nuclear power plant, what's the probability that a meteor will hit it enough times that it could damage it? Very small probability, but by the way, we do have meteors all the time. That's not uncommon. We have meteor showers and meteors all the time, and a lot of them don't hit the ground, but some of them do. And so we had to look at those probabilities because back in the geoscience area. So in quality control, up here, let's go back to our tops. Okay, suppose we keep finding mistakes. We go back and improve the process, improve the process, improve the process. If you do improve the process, and we're using a P-chart, then what's going to happen to these 2.1% defectives? They're going down. 2% to 1.1% to 0.1% to 0.0001%, 1 part per million, 1 part per... Well, when that probability gets really, really small, then all of a sudden, the number of occurrences of these tops are no longer binomial, they're Poisson. Interesting. So, and it can be shown, the binomial distribution from the binomial theorem, let the p go to 0 and n go to infinity in the limit, and in the limit it can show mathematical statistics that the binomial distribution will asymptotically approach the Poisson, and it is a Poisson in the limit. So in the limit it is a Poisson. So the Poisson is a limiting distribution of the binomial. Boom. Okay, but that's why it's important. Okay, and that's what I mean by this here. So that concept is extremely important. You don't have to derive any of this stuff, but understand that when you get better and better and better and better and better, you shouldn't be using a binomial. You should be using a Poisson. Poisson is not difficult to use when you know how to use it. As a matter of fact, if you've taken statistics in a statistics textbook, they talk about the binomial distribution and either confidence intervals or test hypothesis or anything, they'll say, oh, I think sometimes they say when n times p is less than 5, then you don't use it, okay? What they don't say when p is really, really small and n is large, okay, when that relationship gets really small, it's no longer binomial. It started approaching a Poisson distribution. Anyway, it can be shown. Okay, that's enough of that. Let's go on. It's very, very exciting. Theoretical statistics, mathematical statistics, is really cool stuff. You know, it's kind of like, well, okay, sorry, but anyway, it's kind of like you'll have all these distributions: normal distribution, Poisson distribution, binomial distribution. You have the hypergeometric distribution. You have the exponential distribution. You have the beta distribution, the gamma distribution. You have all these distributions, right? There's 10? No. They're all the same. They're a family of distributions. It's kind of like the family and the philia. Anyway, they're all come from an exponential Okay, let's go on. It's late. I got a lot of caffeine in this tea. You know, that probability, what's the probability of getting swamped by a tsunami? Well, you retracted it, but really, that probably was studied back in the 70s. And so you knew when there was an earthquake, let's say over in Java, you knew there was a tsunami coming. But what you wanted to know is how severe is it going to be, like in Southern California, in Hawaii, in Japan, in Korea. So you want to know what's the probability of severity to do the risk. And so that was studied. You're right, Craig. That was really studied. And the Poisson distribution was the occurrences of the earthquakes that causes tsunamis. But the probability then, you had time series analysis. Okay, experiment. Let's do the experiment. Well, this is going to be a little bit easier. Consider the following results of an experiment from a process assumed to be in control, where the experimental design is 20 samples. 20 samples with a sample size of 1,000. Now remember, each sample has 1,000 measurements. Okay? So, samples 1 through 10, 11 through 20. Okay? And here's the number of attributes in those samples. Okay? So now notice there's out of 1,000, I have 1 out of 1,000. The next 1,000, I have 0. This one I have 2 out of 1,000, 1 out of 1,000, 3 out of 1,000, 4 out of 1,000. Okay? I have, here's the biggest, 5 out of 1,000. Here's 0 out of 1,000. So that's a really small probability. They're very, very small. I add up my attributes. 25 and 15 is what? 40. I divide by my total number of 20 times 1,000 is 20,000. I divide by the number in my experiment, and now I get an average proportion of 0.002, 0.2%. So that proportion, 0.2%, is a lot smaller than 2.1%. And so therefore, when that proportion gets really small, that's when you move to a Poisson. Well, some people hope Poisson's a lot easier than a binomial. I'll show you in just a second. And so, well, I'll show you right now. So you bring this down, okay? That's my proportion. But now let's suppose we have a sample size of 850 now, a different sample size. Now remember, we're going to need, let's back up here. We're going to need the mean, again, we need the mean, and we need the standard deviation of the mean. We need those two parameters, right? Or those two estimates. So let's come down here. Okay, here we go. From the sample size. Now the mean is not the average P bar. That's not the mean of a C chart. That's the mean of a P chart. But that's too small to be binomial. It's small, it has to be Poisson. So up here, the average is going to be C bar, the average count. So C bar is the sample size n, which is 850 times P bar. In other words, on the average, how many attributes will we see out of 850? Well, the proportion is 0.002, so 0.002 times 850, on the average, we'll see 1.7. So the average count per sample of 850 is 1.7 of these attributes, of these caps that are defective. 1.7 out of 850. Okay? Okay, that's the mean. The average count. Next, we need the standard deviation of the mean. Okay? Well, here is a really good property of the Poisson distribution. The standard deviation of the average count, the variance of the count is the same as the mean. The mean and variance are the same thing. So the square root of the mean is the variance of the mean. The square root of the mean, and the mean is the same as the variance of the mean. The square root of that is the standard deviation of the mean. Crazy, isn't it? Well, remember up there we had P bar, and the standard deviation is P bar times 1 minus P bar over n. Again, if you let the n go to infinity and the P bar get small, in the limit that P times 1 minus P over n will approach the mean. It can show that in the mathematically too. We won't do that though. Okay, now so all you do is take the square root of that. Essentially, that's all you do. So now I have the mean and the standard deviation. Now I put them together. Here's my mean. Here's my standard deviation. My upper control limit is my mean, 1.7. 3 times 1.3. Again, that's my standard deviation. I'm representing it with 1.3, but I use the entire number when I calculate. Never round during calculations. You can express it as a rounded number here, but use all of the significant figures here when you do the calculations. Okay, and here it is. There it is for the upper control limit, lower control limit. Two things here. One, I round it. I round this to 5.6. That's one thing. The second thing, notice the lower limit is minus, is negative. Well, in control charts, for the P chart, the C chart, and even the R chart here in a minute, you never report a negative value. You never report a negative limit. So if you calculate a negative limit, that's not the answer. The answer is 0. So be very careful, and I'll have that in the homework, which I'll open up here in a minute, and I'll show you what the homework is. So if it's negative, that's not the answer. The answer is 0 for the P chart, C chart, and the R chart coming up here in just a second. Okay, now we move on to monitor production. Here's our 850 again, and the same thing applies as we did before with the sample sizes. So up here, this sample size of 1,000 here for 20 samples. So I have 20,000 measurements in this experiment. That sample size was to estimate the parameter with the smallest amount of variance as possible. This sample size of 850 is for production. Okay, and here's my 0. And notice that this is truncated here. 0, 1.7, 5.6. And now out of 850, there's 2, 3, 1, 4, and there it is right there. Ding, 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 ding. And notice this is asymmetric. Well, two things I want to mention. This is asymmetric. Why? Because it's symmetric around the center line, but you never report a negative limit, so that is truncated up to here. So a control chart could be asymmetric, and here it is. When it's on the line here, it's in. So you cannot violate the lower limit when it's 0 for a C chart or a P chart or an R chart. That's the lowest it can be. Okay. The same thing applies. The decision rules, the same thing applies. Method of assignable cause applies. Quality control program same thing applies. It applies to all these charts. Now, once the experiment has been performed, the parameter does not change as before, but different control charts may be constructed for different sample sizes using the same parameter as before. Consider the examples below where the P is from the experiment and the sample size n is given. So now my P is 0.002. Okay, now my sample size, again, I'm increasing it 500, 850, 2350, 5200, 7250. Now, as I increase this, notice as n increases right here, since the center line is a function, is directly related to n, my center line is going up. Okay, center line stayed still, and just when the sample size increased or decreased, the size of the chart changed. But for the C chart, the actual center line increases when the sample size increases. But if that increases, the standard deviation also increases. So not only does the center line increase, but the chart gets bigger. Interesting. And so over here, this is down to 0, because negative, negative, negative gets 0. And then I get positive here. And notice this is, now notice when the sample size goes up, the size of the limits 4, 5, 11, 19, 22, it gets bigger. So for the C chart, it's directly related to the sample size. Not only the size, but also the location. Because you're counting. You're not standardizing the counts. It's the raw, absolute number. You're counting. Well, the proportion, you're counting it. You divide by the sample, and so you're normalizing it. And it's ranges between 0 and 1. It's a proportion. So since you normalize it, the larger the sample size, it decreases the size of the for the P chart. For the C chart, when the sample size increases, since you're not normalizing, you're counting it, it's going to grow. In the real world, I think you guys can see this. In the real world, what determines the number of samples and sample sizes in the experiment? Good question. An easy answer and a very common answer is your budget. Is your budget, your resources, and the time and how quick you have to have it done. And so how much money do you have? And you want the largest sample size possible within reason. Okay? And so like up here, so 20,000 samples says that's pretty much all our budget can handle, and we need to get it done by. See here we're in where are we in April? We have to get this done by June 1st, and so well it takes time to do all these things, and so 20,000, but all we can do resources, time, money, budget, and that's usually the initial decision. Now within that, the sample size in the experiment should be as large as you can make it, as big as you can make it within reason, because you want that estimate to be as lowest variability, the smallest variability possible, and that's usually how that works. Okay, go ahead and keep asking questions, Craig. If you have any more, I like them. One thing about the reason I'm talking about this is that this is an introduction to control charts. Okay, well, a lot of what happens. Notice if the sample size changes here, the size of this chart changes. And so what happens a lot of times, people say, you know, I can take in the production process. This is the production. In the production process, I can take any sample I want. Okay, it's coming off before I package it. I can have any sample size I want. Well, what sample size do you want? I want to make it easy. As a matter of fact, I want to make the chart easy. I want the size of the chart to be exactly 10, 5 and 5, 5 above, 5 below. So what should the sample size be to make the size of my chart exactly 10? Well, it's somewhere between 850 and 2350. Because this is, I take that back. Somewhere between, 850 and 2350. Okay, and so chart design. So you design your chart, the chart a certain way. One way to do that is you know your proportion, and you select a sample size such that your chart is exactly a plus or minus 5. So that's a lot. That's a lot of how people do it. We don't get into that here. It gets interesting. And also you can, if you look at it, to solve those things, it's nonlinear. And so you can iterate to it when you get a complicated problem. But that's beyond this course. Okay. We have 2 more to do, then we're done. So, data analytics meet budget constraints, if that's a metric. If that's a metric coming down the pipe, well then okay, we'll put that in our mix, and all of a sudden we will look at the budget, we'll look at the cost, okay, if that's on the mix. So, and sometimes the cheap can justify your existence too. Sometimes you want to do that. And if you need a lot of money, they don't want to pay for it, then you don't talk about the value of it. You talk about how much you're going to be hurt if you don't do it. Okay, and that's a little bit more in negotiations. Which, by the way, that's very powerful, because a manager, a president, or a VP, or a C-level person, they're okay if they're not as good as they could be, but they don't want to look bad. So you don't have to say, oh, if you do this, you'll be better. You should say, if you don't do this, you'll have egg on your face. It says, okay, well, we're going to do it. So that's how you know. That's how you negotiate metrics, and you can have data. You can have descriptive analytics and all this really pretty stuff to really emphasize that point, because you can make those numbers say whatever you want, and that's not unethical. That's business, because you're not saying anything wrong. You're just making an argument. I guess this course really should talk about ethics too, because look what we're doing here. There should be ethics, communication, but also ethics. If you can communicate, anyway. I could go down that rabbit hole, but I won't do it. We only have two left, then we're done for tonight. Okay, this has been fun. This is really cool stuff. Very useful, very powerful. And you can keep on track. As it actually, Walter Schuhart at Bell Labs, and also Walter Deming out of Bell Labs, they made a career out of this stuff. And anyway, they did a lot of quality control. W. Edwards Deming out of in the automobile industry and everywhere. GM, everything. M&R charts. M is mean, R is range. These go together. Now, the M&R charts are used to detect anomaly in the mean and range of a given variable. Now we're moving away from attributes. We're going to variable. Okay, now it's continuous. From a service operation manufactured product, these 2 charts are usually used together. The data are assumed to be drawn from a normal distribution. The M chart is called the X bar chart or X bar chart for sample mean. I'm using M for mean because I have P for proportion, C for count, R for range. So it seems logical to me to say M for mean. Okay, but a lot of times they have an X bar in there. But it's a sample mean, that's all it is. Consider the results of an experiment from a process assumed to be in control again. Okay, here's my experiment right here. So now, notice I have 10 samples, 4 measurements per sample. So the question is, what's my sample size? Well, my sample size is the number of measurements per sample, so it's 4. Or you can look over here, I said sample size is 4. So from the M&R chart, from the experiment, we want to pull off 3 different parameters. 1, 2, 3, 3 different parameters. Okay, now notice up here, we just had one, and the C chart, we just had 1 parameter. The P chart and C chart 1. But for the M&R chart, we have 3 parameters, 1, 2, 3, okay? First is the sample size. The sample size turns out to be a parameter, because that sample size in the experiment will be the sample size in the chart. So they're the same with the M&R charts. They don't have to be the same for the P and C charts. The sample size in the experiment and the chart could be different. But for the M&R charts, the sample size in the experiment and the chart are always the same on this development. There's different ways you can get around it, but not here. Okay, sample size. 2, the second parameter is the grand mean. That's the average of everything. So there's 10 samples, 4 per sample. So there's 40 numbers here, isn't there? There's 40 different numbers. So we're going to sum everything, 6160, and there's 40 numbers here. So 6160 over 40, the grand mean is 154. The average of all of these measurements are 154. Oh, for example, so instead of the cap on or off, suppose now we're measuring ounces. Well, that's not 120. That's 20. This is like 22 ounces. Anyway, suppose it was. So this is about 20 ounces, and this is 12, 19. It's close to 20. So it's in here somewhere. Anyway, the point is, or let's say grams. That's easier. Measuring something else. So it's a variable measurement. It's a ratio scale. Well, usually ratio. You can have interval, but usually ratio is better. Okay. Now this grand mean, that 154, the grand mean M bar, see the M bar? This is going to be the center line of the M chart, because the M bar. Center line of the P chart is P bar. Center line of the C chart is C bar. Center line of the M chart is M bar. That's why I did M. Okay. And the third parameter is the average range. Okay, well, a range is the difference between the maximum and minimum value in a sample. So right here, the maximum of these 4 numbers in sample 1 here, the maximum is 194. The minimum of these 3 numbers is 110. And 194 minus 110 here is 84, and that's my range. I do it for the second sample. Well, the maximum is, let's see, 192, and the minimum is 130. All right, yeah, 130. 192 minus 130 then is 62, and that's the range of my second sample. I get the range for every sample. There's 10 of them. I take the average, I add this up, 700, there's 10 of them. I divide by 10, and my average range is 70, and this will be the center line of my R chart. So the parameters represent my center line. Well, it did in the P chart too. P bar was the center line. Now, M bar is the center line for the M chart. R bar is the center line for the R chart. Now we just need the standard deviation. Standard deviation of the mean. Okay, well, down here, let's construct the charts, and let me show you how this works. Okay, down here is where we start constructing the charts. This table here, here's the center line, and there's the 154 and 70. So I copied them. I just copied those down. There they are. And then here's the upper control limit and the lower control limit for the M and R chart. Okay, so now let's let me show you how this is done. Let's start with the upper control limit for the M chart. Let me shade this in so we know where we are. There we go. That's what we're doing now. Okay, now what is this A2 and R? Okay, the what's going on here? Let's do this. So the definition of a control chart is M bar plus or minus the standard deviation of M bar. Okay, so three times. So this right here represents the definition of the upper control limit. Okay? In other words, it's M bar plus 3 standard deviations of M bar. Now, in this development, and this is common, they do not use the standard deviation of M bar. Instead, because the standard deviation is a measure of variability. Instead, our measure of variability from our parameter is the average range. Here's our measure of variability, range. So here they say, okay, I'm going to take this term right here. I want to replace that with a term that is approximately 3 standard deviations of the mean. Okay, well, what we're using is R, our bar, our range. So what do we multiply the range by in order for this number to approximate 3 standard deviations of the mean? Well, this A2 is a coefficient that was determined, about a half a century ago, back in the 50s, or back in the 40s and 50s, when they started doing all this stuff by hand. And they're still used today, but it's all automated. So, for example, they say, okay, well, how'd they come up with this A2? And what is it? Well, you can see down here it's 0.729. There it is. But where does it come from? Well, they estimate it. It's calculated years ago, like let's say, for example, a simulation. They say, let's take 10,000 samples of size 4. On every sample, let's take a mean, a range, and the standard deviation of the mean. And let's plot the range here versus 3 standard deviations of the mean here, and plot these things and do a regression and say, oh, if I multiply the range by this A2 number, this will estimate 3 standard deviations of the mean. So I did like a simulation. And I've been thinking of, every time I talk about this, I think of actually just demonstrating a simulation of doing it, just to illustrate that. Because today, like in Excel or Python, or you can do simulations pretty easily. Just do 100 points at 500 points, something like that. But I didn't. But that's how they did it. So what is that A2? Well, the A2 comes from the table down here. Now, this table is not my table. It's an industry table I copied. I don't have anything in here that says it's an industry table. So there's no danger of copyright infringement because this thing it's got to be fair use because it's over 50 years old. Anyway, 60, 70 years old, I don't know. Anyway, so A2, but then which one of these A2s do I pick? The A2 I pick is on the sample size, n equals 4. And that's why the sample size is a parameter, because you're going to be using the mean here is the center line. The range here is the measure of variability. The A2 here for the sample size is a coefficient that estimate the variability, which is the 3 standard deviations of the mean. And then you multiply those, add them, and there's your upper control limit. That's really all there is to it. So that's really the concept. That's how they're doing this and why they're doing it this way. Now over here, the lower control limit, you just change the plus sign to a minus sign. That's all you do. Okay, now what about the R chart? Well, the R chart is similar. It's very, very similar. Okay, let me take this here. See if I can do this right. Oh, I didn't. I'll do it below. Not doing very good here. Yeehaw. There we go. Now let's bring this up. Let's make this a plus. There we go. Okay, let's make this an R. Whoops. Let's make it an R. Well, that's a, what is that? That's an R. It's a P. Oh, it's Greek. Sorry. That was a Greek that was a Greek row. That was row. The Greek thing was on. P is a capital row. Anyway, it's a row, it's not P. Again, it's R bar 3 times the standard deviation of R bar. Again, that's the definition of the upper control limit of R bar. Okay. They go through the same process like we did before. We want to estimate that using range. By the way, a lot of people say, well, this doesn't make sense. R bar is a range, but how can you have a standard deviation of a range? Well, the estimate is a random variable. Any random variable can have a mean and a variance, usually. Okay, and some theoretical distributions don't, but all these do. So the standard deviation is a random variable, an estimate. And so a standard deviation can have a mean and variance. The variance, the sample variance is a random variable. So it can have a mean and variance. So you can have a variance of the variance. You have a variance of the mean. You get variance of the standard deviation of the variance, and standard deviation. It gets confusing. Got to be really careful with the language. It gets kind of fun, actually. You start, in other words, you have to think about it. You start mixing them up, and then they go, what does that mean? I don't know. You know, well, you can if you figure it out, but it does. It's more trouble than it's worth. It's getting late. Getting into this. It's been a busy semester. But notice R bar is in the measure of variability, and R bar also is in the center line. So here they said, let's put all of this together. Since R bar and R bar is R bar, okay, it's all a function of R bar. It's all a function of the average range. Again, they did the simulation. They estimated a coefficient D4, and D4 is here with a sample size of 4, 2.282, and there it is. And so there it is. And then the lower control limit, that's different. That's going to be D3. In this case, it's 0. In other words, I can take this again and say this. Okay, bring this back up. Okay, and so it's the same thing. Okay, you put all this together and it's a D3. And notice that the D3 is all 0 until you get to a sample size of 7. Why? Because an R bar cannot be negative. Down here they've already rounded up to 0. This is industry tables, not my tables. They've already rounded it up to 0. Okay, so the P chart, the C chart, the R chart cannot be negative. The M chart can, the mean can, because if you measuring the ambient temperature in Fahrenheit of Antarctica in the winter, it's all going to be negative. So the average is negative, the upper and lower control limit's negative, so it can be negative, but you can't have a negative count or a negative proportion or a negative range. The interval of a range, the minimum is 0. Okay. Anyway, that's how you calculate it. And then down here, you monitor production. There it is. Here's my 4 items. On each of these items, there's the mean and there's a range. I plot the M and the R down here. There's my M and there's my range. You can see that I actually plotted these numbers. That's exactly what they look like. Ding, 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 ding. So they all look pretty good. Not too bad at all. Now remember, up here at the very beginning, I said these two charts are usually used together. And the reason is because they give different pieces of information, but they all come from the same data set. So the M bar is like an average. It's like a center. It's like a measure. Okay, and so right here, the center line. This center line here is kind of like this is the target value. Okay, and if you're measuring something above it or below it, it's kind of like the center line is like this is what you want. Above it or below it, that difference is usually observation versus some estimate, because that center line was estimated, right? So an observation, the difference between an observation and an estimate of that observation is a bias or residual or variability or deviation. So the M chart is a measure of bias. How much bias do you have? Well, the average bias here is pretty darn good. It's right around the center line. But if it's up here or down here, or go above or below, then you have bias in your data, in your variable, in your quality characteristic, which is a variable. What about R? Well, R is a measure of variability. Now, remember back in time series analysis, variability was MAD, mean absolute deviation. Well, the absolute deviation of that, another way to look at that is the range. A range is also an interval. Well, the absolute deviation is a measure, which is a single power measure. Okay, single measure. It's not a second power, third power. It's a single power. A variance is second order measure of variability. This is a first measure, and so our range is the same thing. It's a range between two. So the range is a measure of variability, which is a measure of risk. Okay. Now, the bias up here and the variability or risk down here, they have different names. Sometimes people call this bias. Sometimes they call it accuracy. Accuracy. How accurate is it? Down here, range, sometimes people are calling this variability. They'll call that reliability. Okay, or repeatability. How much variability is there? So they have different names for the different things. And so these two are used together. Okay, so to illustrate this, I don't have, to illustrate this, I didn't do this. Usually in class I have a blackboard. Let's see here. Anyway, oh well. This is it illustrates bias and variability. I think I've illustrated that before, maybe. So I'll just stick with this. Tell you what, I kind of want to do this. This is the last thing we'll do. Okay, we're almost done. But bear with me if you will. Well, if well, you don't have to if you don't want to. But anyway, let me do this. Let me do a. This is kind of on the fly. Okay, here we go. Okay, now suppose we have this is my DART experiment, my DART. Oh, I did it wrong. Okay, 4 people. Make sure I get this right. Let me do a bunch of them. So 4 people have 4 darts. There we go. Okay, and let me enlarge this. Enlarge this. Okay, I think I have it right. Center these, center them. Yeah, I did it. Okay, now let's do this. Sorry guys, I should have set this up before, but I didn't think about it until I started doing it. I probably shouldn't do it, but I'm doing it anyway, right? Let's just do it and not think about it. Bottom, left, okay. Okay, now I need these. Let's do it this way. Here we go. Now then, I need to do this, make this heavy, and it'd be a bottom and a left. There we go. It's a top, and this is a right. Here we go. Okay, 4 people have 4 dots, and each one is going to try to hit the center, like person A. This is person A. This is person B. This is person C, and this is person D. Here we go. Okay, now person A gets 10 dots and goes bing, 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 and tries to hit the center here. Okay, so let's take a shape here. Let's say okay, and they're pretty good here, and that circles represents the shape. Okay, let's take the no fill. That's good enough. Okay, so that's the first person. They did pretty good. Okay, now the second person over here pretty much did this. Well, they're pretty much on target. They're hitting the target, but they have a lot of variability. Okay, this one's on target and it has small variability, right? Okay, now this one down here has a small variability, but it's off target. It's over here. And then the fourth one down here, come on, you can do it. This is down here. This is way off the track. Okay. Now notice, here's my target. This is on target, low variability, on target, high variability. This is off target, low variability, off target, high variability. Okay. So let's look at bias versus variability. Okay. This C and D both have a bias. Oh, let me go ahead and put this in. Insert table, oops. Insert home. Oops, let me take it out. Shape. Let's do this. To there. They didn't like that. Okay. Good. And then put this over here. So this arrow represents the bias. And this right here represents the variability. So this has a lot, so B and D have a lot of variability, right? And A and C has low variability. So this is very good reliability. Well, A and B have very good validity or accuracy, okay? But C and D has a lot of bias or inaccuracy. But A and C has good reliability and repeatability because it repeats, and B and D has very poor reliability or repeatability. Okay, and so when you see the M and R charts in control and out of control, when the M chart is in control, you're right here on A and B. When the M chart is out of control, you're C and D. And you look for those kinds of method of assignable cause. When the R chart is in control, then you have A and C. When it's out of control, you have B and D. And then you look for those kinds of methods of assignable cause for in control and out of control, or out of control, actually. Too much variability. The R chart's out of control. Okay, and so then you go back and say, well, what are some of the causes? Well, when you have a bias that's in control and out of control, or the variability in control out of control, well, that will indicate different types of things. Usually bias is calibration. it's calibrated wrong. Okay, you're measuring up here instead of down here. That's usually an easy fix. You just calibrate it, zero it in, boom, you're good to go. Variability, okay, that's a little bit tougher. Especially B, everything's all screwed up. But B, the variability start, maybe that's fatigue. The fatigue is maybe you just need maintenance. You need to maintenance, to upgrade it or to preventive maintenance or whatever. So if you can bring it back, and then your time between maintenance is too large, it's too long. So what happens is the R chart, the M chart stays in control, but the R chart goes out of control. And so if it gets out of control too much, you say, well, my time between maintenance need to be shorter, because it'll start going out of control, but I don't want to get too much out of control because it starts impacting my quality. So this is how these charts can be used very effectively in looking at monitoring things. And so this goes a little bit deeper than just an introduction, but it kind of opens the door to a lot of analyses. Okay. Actually, Craig, I want to make one more comment about your comment. So data analysts meet budget constraints. Well, a data analytics person could argue, well, if you do data analytics, we can save you enough money to where it's going to be negative. I mean, we save so much money that it cost you less than if you didn't use this at all. Okay, it'll cost you more if you don't use this. Anyway, so it's not that we're lowering the cost that we're making you money, and that's so that you want to make that argument too. And the way you do that is you go for the low-hanging fruit and do the first things first. That's easy, or 2, that has a lot of visibility, or 3, that lowers the cost significantly. And it's nice if you have all 3 of those at the same time, and that's kind of a nice situation to be in. Okay, well, that's all I have for today, and that is going to be your that's quality control. And actually, this is the end of the material for this course. Next week is the spring break, and after that is review. What I've tried to do in this course is give you a lot of foundational stuff, a lot of really practical things that can be used anywhere and everywhere. And even if you don't use the quantitative stuff, you know it can be done, and you know that you know what the concept behind it and what it's going to do for you. Okay. Okay, good question, Becca. It's a good question because you reminded me. I was going to do it anyway. When will Quiz 8 and the project assignment be posted? Is it possible for them to be posted a little early so we can start working on them? It's going to be posted right now. It's going to be posted right now, and I'm going to show you how to work them. In other words, as soon as I get done, I'll post them. And this is the first question. The first question: an experiment was conducted on the quality control of length. Okay, quality characteristics of length. The measurement of each item here is recorded. I'm sorry. I want to interrupt myself. Craig, I showed the EV to my boss, and now I have a new project to work. You know, I was talking about that the other day. You know, if you want more work, then you can, all this stuff. All this stuff, you know, if you start doing it, they'll go, do it. You'll be all kind of projects. And so how do you get around that? Is as well, if you want it done, but you don't want to do it, tell someone else to do it, you know. If you do this, you can get this, you know, try this and see if it works. They'll try it and then they get the project. Because this stuff is not hard to do. Some of it you want to do. Some of it you don't really want to do. Anyway, there's a way to do it. Okay, here we go. Construct a chart using a sample size of 7. There's 7 of these things. Now, use a population variance. What's the upper limit, center line, and lower limit for this process control chart? One of these is right, I'm pretty sure. Okay, good. Well, this should go pretty fast, especially from this lecture here. I'll be talking about this here in the next 10 minutes here. Okay, now, how do you do this? Where you do this is in this first video right here. And I want to show you. Let me click this video. Let me mute myself. Let me come over here. Let's see where it's at. Here it is. I think this is it. Yeah, on 740. Construct a simple process chart. Right here, I have 1, 2, 3, 4, 5, 6, well, whatever sample size this is. Can't count right now. Sample size is 8. This is 7. Here's the mean and variance. Da-da-da. That's how you do it. This right here explains exactly how to do question number 1. Okay? There's question number 1. Now, if you want to, in order to do it, let's bring in Excel. Take this right here. Control C and copy that thing. Control C and copy. Bring Excel back. Put it right here. Paste. Now remember, what you need is the mean and the standard deviation, right? And this is going to be average, and this is going to be standard deviation dot p. That's what you use. So this equals the average of all of these numbers. That's the average. Did I get them all? Doesn't look like I did. I guess I did. And then this equals a standard deviation dot population. P is a populate. Oh, let me make this big so you can see it. Well, I can't right now. Let me make this big so you can see it. There we go. That's the average. You see, I took the average of all those numbers. Oh, wait a minute. Let me make sure. Average of all these numbers. And there's this. And this is the standard, standard deviation dot P. It's a population. Statistics, quality control, statistical quality control, they use population standard deviations and variances. They don't use sample, they use population. And all you do is you get this right here, return, and that's going to be your standard deviation. Okay, I won't do it for you. And then it'll simply be equals this plus 3 times this. For the upper control element, that, and then it'll be this minus 3 times this. And that's what you do once that's in there. So 84.3. Wait a minute, that doesn't look right. It isn't, it's not right. What happened here? Wow. The very first one. This is not. Let me look at this for a second. Did I do it right? The answer should be there. Sorry about this, guys. That doesn't look right. Wow. Okay. I think I know what's going on. Wow. This is really annoying. Okay, here we go. Control C, copy this thing. Okay. Let's bring Excel back. Here we go. And let's come down here. And let's put it in here. There it is. Copy this, transpose it, okay, and then that way make a vector out of it. And let's see. I think the average is supposed to be 84. It should be 84. There it is. Can't do rows, got to do columns, column vectors. And the same, standard deviation dot p, and now do it. And that's how you do it. Okay? Does that help? That's how you do number one. Well, let me, I got my thing here. Okay. And then now, all these are the same. All these are just, it's 2 through 5. There's only 5 in this homework assignment. And here's what I want to go over. This is a practical example. The machine that cuts metal holders for electronic pencil sharpeners is being monitored with statistical process control charts. Use experimental data below to determine the center line, upper control limit, lower control limit for each of the control charts M, R, C, and P. You're doing 4 of them. Assume the sample size for the experiment and for each control chart is 6. Let me highlight this and make it big. It's 6, which is the number of metal holders per sample. Which is the number of metal holders per sample. Remember, a sample size represents a number. It's a number of metal holders. These are metal holders. A lot of people say that's sample 1. No, a sample 1 is the number of metal holders. And so the first 6, there's your first sample. That's sample 1. And then 7 through 12 is sample 2. And then sample 3 through 18, and then sample 4. There are 4 samples, because these are the actual numbers. It's the reason it doesn't work in Excel is because the function, the macro, assumes you have columns. Okay, it doesn't assume you have rows. So you have columns, and it'll do multiple rows if you have it in a column. But for some reason, it doesn't do rows. It's just an idiosyncrasy of Excel. Okay, but you can do them if they're stacked, but not just a row vector. You have to have a column vector. You can have a matrix and a column vector, but not a row vector. Okay. Okay, so you have 4 samples, right? And then construct the P chart for defectives per lot. A C chart for the number of defects per lot. The M and R chart for the average length per lot. Okay, now the difference between a defective per lot. Defective means an item is either defective or it's either good or bad, binomial. A defect means how many defects do you have? You count up the defects. Usually defects is a C chart plus on, and the defect is a P chart, which is the number in a proportion. The M and R chart is the average length per lot. Okay, although the data set from the experiment is small, assume an item is defective only if the length is greater than 23 millimeters or less than 15 millimeters. So I define what defective means. Okay, so right here, I'm going to take this here and say, I'm going to say defective. And come down here and count. Greater than 23, less than 15. Okay, oh, there we go. That's defective. Less than, so you count up the number of defectives. Less than 15. Hello, bingo. Whoop, bingo. So you count up all these, and down here, you sum them. Okay, we don't know what it is yet. I'll let you count them up. Okay, and that's the number. So you're calculating the defectives. You're counting them. And then I say, an item contains a defect only if it violates any of the set of quality characteristics. I've already mentioned that. The set of quality characteristics is not given to us, but the number of defects for each item has been determined and reported in the table below, which is right here. There's 1, 1, 1. I don't think I put more than 1. You could have had 2, But boy, these are really small, aren't they? So you count up the number of defects and you put the sum right there. So now you know how many defectives there are and how many defects there are. Okay. Note that a defect in an item does not cause a defective item, and a defective item does not cause a defect in the item. Keep the number of defects and defectives separate because the definition of a defect is different than a defective. In determining the control charts, construct each sample with consecutive item numbers beginning with 1. That's what I mean. 1, 2, 3, 4, 5, 6, there's sample 1. 7, 8, 9, 10, 11, 12, sample 2. There's sample 3, and there's sample 4. Okay? And here's a number of defects, and there's a number of defectives. Okay? Let me say number 1 and number 2, tweedledee, tweedledum, number 2 there. Measure number 1, measure number 2. Anyway, and then down here, let me go ahead and put this down to show you how this works. Now we want the P bar. P bar. Right. So let's bar it. Here we go. P bar. And what is this going to be? That's going to be my number 1 divided by the number in the experiment, which is 24. And this is the number 2 divided by the number in the experiment, which is 24. Okay, hopefully you're seeing what I'm saying here. So there's your P bar and P bar for your P chart and your C chart. Okay. Now next, and the sample size is 7, right? In a 6. So let me put that here to make sure you know that n equals 6. Well, n equals 6. Bingo, bingo, bingo. That's important. Okay. Now notice the M&R chart is the average length per lot. Okay. Well, therefore, what you're going to need is the average. So let me bring this down again. I want the average, which is going to be the average of all these numbers, average from the experiment. So boom, that average is going to be the average. That's let's go ahead and shade that. So I get this number, I calculate that number, and then these are going to be my parameters. That's going to be my average. And what else do we need for the M&R chart? We need the sample size. The sample size is 6. We need the average. The grand mean is this. And then we need the average range. Now it's the range within a sample. So let's bring the range over here. Let's go right here and then just say the range. Okay, but this is the sample. So what's the maximum length? What's the maximum number in this sample? Ding, 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 26. Is that the maximum? 1, 4, 5, 2, 5. 26 is the maximum. What's the minimum? Well, the minimum is 21, right? So what's the range in this? It's going to be 26 minus 21, which is 5. Is that right? Yes, it's right. I'm pretty sure it's right if I did my arithmetic right. I did the subtractions right. You do that for this one. You do that for this one. You do that for this one. And you take the average right here. And that's going to be your average range. Now you have the 2 parameters here. You have this one and this one. And now you have your sample size up here. Now you have everything you need to construct your charts. That's how you do this problem. Okay? Oh, and then you look up, for a sample size of 6, you look up to 6, you look up the charts and the coefficients. Okay? Now remember, why not? We're here, let's just do it. Let's just go down again. This one, see, what is this? This is D, A, this is A2, and this will be D3 and D4, and the sample size is 6. Let's bring back my, I probably don't need to do this, but let's bring this back. Where's my sample size of 6? Sample size of 6, here it is, right here, those 3 numbers right there. Let's just Control C these babies, and let's get that done, and let's just put it over here. Go bingo, and there it is. That's your A2. This is your D3 right here. This is D3 right here, and that's D4, 2.004. That's all the numbers you need, and that's how you do this. And then down here, it's going to be, there's one of these is right, one of these, one of these, one of these. Boom. So that's this homework, and that's how you do it. So hopefully that will help. Okay. Now the other thing is that the EVA is done this weekend, but I know a lot of people have already turned it in. And if you have any questions, you can ask on the board here. But I think that's pretty straightforward. And also, again, the videos here on the EVA, right here, this EVA video 3 in Excel, that's more than enough you need to solve the homework for the EVA, if I remember right. Okay, I'll pause a little bit, wait 5-10 seconds. If you have any questions here before now, and next week is the spring break. I will pause here and say, does anyone have any questions? Has this been good? This will be recorded. I'll post it tonight. You'll have it. I'll post the homework tonight. You'll have it. And so you can actually get all this done probably tonight if you want to. Yeah. You're welcome, Kat. Actually, I don't really plan to post the project, the outline, because it's not that much of an outline really. It's just whatever you're interested in, whatever you want to do. I explain it in the syllabus, and I have examples in my down here project list. These are just suggestions if you're interested, or you can do anything you really want. I have different lists down here. If you want to pick one of these, something that sounds interesting to you, and really, I just want to do something that that you're interested in, that's beyond this course, and something that you would like to do. And so, it's more for you than me. I want you to do something interesting. I don't want you to do something that's not interesting or that's not part of operations. But use this as an opportunity to go deeper, broader. Some people use a case study from their work, and that's perfectly fine. They apply this, like Craig. You're doing EVA. Maybe if you have a problem where EVA can be applied and see how they would use it, that could be a project right there. Because Craig said, you said you showed, now you have a new project at work. That could be your project. Do it at work and just double dip and just put it the project here. I just want this to be an opportunity for you to use this material beyond just me teaching it. You to use it in something where you're learning something on your own. And that's kind of like a bridge between the course and you start working out there in industry. Do this, learn how to do this stuff. And now's the best time to do it, because it's fresh in your mind and you have all these examples and you do it once, you go through the process of doing it. And then that process is part of learning how to apply this material. And so that's pretty much what I'll be saying after the break and the review. But I'll do in a video and I'll have explanations, and that's pretty much all I say. And the exam review, I'll show you the types of questions, where to study them, how to prepare, and I'll show you details. Basically, I just want everyone to if you look at the video and you have good preparation, then that exam should go pretty fast. And I'll show you exactly the kinds of questions that you'll be asking. Do we do it in a group? No. Well, Simba, our Simba. Do we do it in a group? Good questions. You can do it in a group, but each person must do a project individually. Do it individually. But notice what I have here in my website. Like forecasting. Suppose, where'd it go? Here it is, forecasting. Suppose you get a group of 4 people. You're one of 4. All 4 of you want to do forecasting, right? Okay. Well, right here you can get this book. Let's go ahead and click on it. What is it? Oh, a very practical book on forecasting, right? And you say, okay, well, chapter 4 could be one person, judgment. Chapter 8 is ARIMA models. Chapter 5 is nonlinear models. And chapter 2 is graphics. Okay? Or if you want to do process management or business analytics, sustainability, or a lot of people do sustainability, or quality management or project management, this kind of thing, or supply chain. So you can just do, so here's 4 people in each one of these. Or when you have this book here under forecasting, these are just 4 chapters. There may be some of these other chapters you might take and do something that I don't even put here. It's pretty much up to you, something you're interested in. So each person does an individual one. But you can help each other out. And you can work together and to say, okay, I'm doing this one, you're doing this one, you're doing. Everyone writes and produces and creates their own videos in your project. Again, I want this to be a takeaway for you to say, here's what I did. Not here's what my team did, or here's what someone did on my team. Here's what I did. So when you leave here, I want you to take something like that away with you. And that's my thinking. I think that's very valuable. You have 2 or 3 weeks to do it in. And you can start, and then when I have in 2 weeks, when I have the video, and I'll have a class every Tuesday night anyway. It won't be long, but it'll just be Q&A, question and answer. I'll conduct class for 3 times. And you can ask questions about it if you want. But you can only take the exam 1 time. It's not best of 3. You can only do the exam 1 time. Good. Any other questions? Well, that sounds really good. It sounds good because I don't hear anything. Hearing nothing sounds good. That means you're on track. If not, use Q&A. I'll be looking at it this week to see if you have any questions. And I have office hours Thursday night at 7, Friday night at 7, office hours Zoom. And because it's no longer Monday, Wednesday, Friday, or Monday, yeah, because Wednesday night I have class now. I have another class. So, good questions. Thanks for sticking with me. And I hope this helps. I think this is all it's going to be for tonight. That's all I have for tonight. And between now and next time I see you, I want to urge everyone to stay safe.